laboratory consolidation test, a test we use to study the consolidation process of the soil. And how we study consolidation from such a test, it is we should about avoid the ratio pressure plots. This is the final results we got from consolidation test. We say that in the consolidation test, a one-dimensional consolidation test. Why we call it one-dimensional? Why we call it one-dimensional? Why we call it one-dimensional? What? I mean, we say that one-dimensional consolidation test, right? We use one-dimensional consolidation test to study the consolidation of clay, consolidation of soil. So why it is one-dimensional consolidation test? We don't know. Anyone know?
Maybe it was like the first one.
Not exactly. That is part of the reason. But one-dimensional, what that means? The meaning of one-dimensional is not only because that we apply the load vertically. It's just because that the soil can't sway horizontally. You can imagine that if there is no stainless steel ring, if there is no constraint of the ring from the ring, we put the soil in the stainless steel ring, right? If there is without the ring, you apply a load from top vertically. Yes, still it's not a one-dimensional. It is a three-dimensional because the soil can be compressed vertically and swelling together. Meanwhile, swelling horizontally, right? It is a three-dimension volume change, right? It is not only vertical. One-dimensional means that the drainage is from top or bottom. What's that? You are a Westfield boy. Okay, we'll wait after the break. We'll wait for you to give something to us. So, okay, let's continue. So, because the constraint of the ring, so actually the drainage is from top and bottom, cannot drainage from horizontal direction, right? So, the displacement is only vertically. It cannot have any volume change of the soil horizontally. So this is why it is one dimension, because drainage is one dimension. The drainage is vertical. The load is vertical, and the sediment is only vertical. There is no displacement in other direction. Okay, so this is one dimension. Why we study it from one dimensional? You may think that for soil, right, soil in field, if you give a load, it can sway, it can have volume change in many directions, not only vertically, right? But as we mentioned, soil is accumulated vertically, right? Soil is not an isotropic material, it is an anisotropic material, but the vertical structure is much more important than the horizontal structure. Yes, you apply a load, but you can imagine that there is a soil block in here and you apply the load vertically. There are constraints from the soil, from the round place of the block, right? Those soil will give a constraint to the soil in the middle. So in many cases, in the embankment, in the underground field foundation, so soil in the horizontally direction is very, very huge, but the vertically is limited, right? The depth we're learning is limited compared with horizontally distance, right? So we can imagine, we can think soil is more vertical than horizontally. So this is why we use one-dimension compression to study the consolidation of soil, right? Because we can compare the soil underground, the soil, the foundation soil, the embankment, the compacted field on the ground into a one-dimensional compression, okay? But we can still study a three-dimensional compression, but it is out of the range of the soil mechanics in here. Maybe later in advanced soil mechanics, or maybe next semester, when we talk about shear strength, we will talk a little about triaxial test. Triaxial test is apply load from three dimensions, from three directions. But in here, one dimension, yes, we can think soil is compressed one-dimensional. That's one thing because why we study consolidation one dimension. Another thing is one dimension is simplify the question, simplify the problem, right? If it is three dimension, the volume change, the settlement will be not so easy to be calculated, right? So in here, because area never change, right? So as long as you measure the vertical displacement, you measure the height change of the specimen, you measure the settlement, right? You can estimate settlement. But if there is no constraint of the stainless steel ring, or it is a three-dimensional, the area is changed, right? So the change of the volume of the soil is actually finally the settlement. So it is much more difficult, much more complex than one-dimensional, right? So void ratio pressure plot, it is much more easier in one-dimensional compression or one-dimensional consolidation. And in here we say that the variable we observed in laboratory in one-dimensional consolidation test is the load we applied, right? Or the pressure we applied, sigma. And the height change of the specimen, delta HT. So you give a load after it reached the equilibrium, after the load, the displacement almost didn't change. That means the consolidation reached equilibrium. Why? Because we say that consolidation is transition between per water pressure and effective stress in soil, right? After all the per water pressure decreased to zero and effective stress increased to the total stress value, consolidation finished. Meanwhile, soil happens some volume change during consolidation. If consolidation stopped, if consolidation finished, there is no much volume change in soil anymore. That means volume change almost finished. That is, when you observe the consolidation process, you can't observe per water pressure effective stress, right? So the thing actually we observed is the height change of the specimen, that is the displacement, how much displacement happened to the soil specimen. If the displacement reached equilibrium, that is no change anymore, that means the consolidation finished, okay? Because the consolidation and the displacement happens at the same time. One stopped, another almost stopped. We can't say totally stopped because there are secondary consolidation, right? But secondary consolidation, we talked a little about it. It's not because of consolidation process. It's not because decrease of per water pressure. It is because with adjustment of soil fabric, right? Right?
Yeah.
So the variable we observed actually is the load we applied and the displacement, right? So under one load, you can observe a displacement after the displacement reach equilibrium, right? That is after consolidation finished under this load. So you have one pair of data, sigma 1 and delta H1. And then you apply another load, sigma 2, and you observe another height change of specimen, delta H2. And finally, with these two pairs of data, we can go to a plot, right? Go to a curve, but we not exactly use delta T in here. What we use is void ratio, but we can transfer the delta H under each loading step to the void ratio change, right? Are you sleeping? No? So you are exactly following. Are you following me? You follow yourself. So we say why these two can transfer. So in here we observe this, right? But we will want to go to a void ratio pressure plot. We not directly use sigma delta H, because we say that we have sigma 1, delta HT1, H1, H1, and sigma 2, delta H2, and so on. We not directly use this. We say that why soil can be compressed, why happens at delta H. That is because void was compressed, right? Soil particle can never be compressed. Only void was compressed. So in here, the height change of the specimen actually express the void ratio change of the soil, right? So this is why we got a void ratio pressure plots, but not a delta H I sigma plots, right? So we want to transfer delta H to void ratio, because we say that void ratio change because of delta H change, right? But how to transfer between these two? How to use the H, the height change of the specimen to calculate the void ratio under each loading step? We talked about it yesterday. In here, we know that void ratio is always the void volume divided the solid volume, right? And if you give a stress, the void volume will always change, right? So actually, solid's volume never change. As long as you calculate solid's volume, you use the total volume minus solid's volume, that is the current void volume, right? But now, volume, we know that volume is a product of height and area, and this is one-dimensional consolidation test. The area never changed because the lateral displacement was constrained by the stainless steel ring, right? So area is always the same. So such a ratio is actually the height ratio of the voids at the soil, at the soil, right? So we have this. Understand? And what is HV? HV is current height. You always observe the height, right? You know the total height. You know how much change of the height, and then you know the current height of the soil, right? You know the current height, and if you know the HS, then you can know HV. You know HS, you know HV, you got void ratio. And as long as you know the different current height of the soil on the different stress level, then you can always check the void ratio change. Understand? So this is actually the clue. But how to calculate the HS? We say HS equals to this. Just to remember this, that's all. HS equals to this. As long as you use in here. What is WS? WS is the dry weight of the specimen. Can you got dry weight of the specimen? Sunshine. Sunshine is not here. Can we go to the dry weight of the specimen? Yes, I'm asking you. Yes? How? You don't know? But you said yes. You must have an idea to go to the dry weight. Think about it. Pardon? Anyone knows the answer? How we got to the dry weight of the specimen? I talked about how we conduct such a test yesterday, right? What we can obtain from the test. What we knew is initial height, soil area, mass, specific gravity. Those data we can always obtain from laboratory. So how we got to the dry weight of the specimen? Yeah? Try, just try. It doesn't matter if you don't know the answer, it's fine.
I think the subject like the initial weight that you take or that you can take from the
Yes, we know the initial weight.
Yeah,
Right now, I want to know the dry weight.
then after you take it, but then you subtract and you get the difference.
No, dry weight is not the difference before.
Like this is like what is the moisture when you have the moisture?
Yes, moisture.
Then and afterwards.
How we use the moisture and the initial weight to calculate dry weight? Can we? Can we go to the dry weight from these two? Right?
Wait, how about is the soil using here saturated?
It doesn't matter actually. It doesn't matter if it's saturated or not. Fuja?
What if dry mass times G?
What?
Dry mass of the specimen times G times the gravity. MS.
MS.
Yeah. Times small g associated with gravity.
Yes, we know MS divided what?
Times.
Times.
Yeah.
Times what?
Acceleration due to gravity. Small g. Yeah.
Now how we got MS?
That's another question.
It's another question. Oh dear. Do you know this? How we got MS?
How much is in the oven?
Huh?
The MS, how to get it? How about,
No, if we use balance, we can directly go to the mass, not to the dry mass.
Oh, thank you. I remember.
you remember?
Oh shit. Yeah, we use that formula to cheers, right?
Do you still remember this? That is, if you know the water content or moisture content, you know the mass of the soil, you use the total mass of the soil divided 1 plus water content, you go to the dry mass of the soil. So this is a very, very basic weight-volume relationship that you should always keep in mind. I said that, yes, you can check the table I give to you to find the right equation to do the calculation, but this is the most simplest and the most important one you should always keep in mind. Because in laboratory, what we got is a total mass, right? It is a weight mass. it is easy to use a balance to go to the weight mass, and it is easy to use the oven to go to water content. So how we got dry mass, dry unit weight, right? That is first, you need to go to the dry mass, right? This equation actually tells you that we excluded the water from so much soil and how much of the solid particle, right? So water content, it doesn't matter if the soil sample is from field or you compact it, you can always water content, right? We know the water content. If you prepared the soil, you must prepare the soil into some water content, right? You know the exactly water content. And you know how much soil you used to compact the specimen, into the stainless steel ring. Then you know the total mass, the weight mass, you know water content. You can got the dry weight or dry mass, it doesn't matter. These two can be transferred into each other with gravity, right? The small g, right? Area, we know this. GS is specific gravity. And this is unit weight of water and density of the water. We all know this. You can use this equation or use this equation, it doesn't matter. But we can definitely, with some initial data, we can calculate HS. That is the height of the solids, right? If you know the height of the solids, you always observe the current height of the solids, right? You know H, and then you know HV. You know HV, you know HS, you know the current void ratio, right? You know the void ratio under the first loading stage, and then second loading stage, third loading stage. Finally, you know some pairs of data, then you can got a void ratio plus. In here, it just gives you a figure, tell you change of height of specimen in one-dimensional consolidation test. Let's see. So if it is a saturated soil, right? In here, this is HV and full of water. Yes, you say that the initial soil diagram may be like this, but if we separate the solids and the water, right? We can go to this and this. We can actually separate the soil into these two parts. One is the solids part, another is water part, full of voids, right? So the compression, maybe under the first stage, under the first loading stage, sigma 1, we give sigma 1. You have a compression of delta H1. This delta H1 is actually the void ratio, the height of the void change, right? And again, you give another stress, sigma 2. We got another compression, that is delta H2. Again, this delta H1 and delta H2 are all from the change of HV, right? So actually, current change H is caused by compression of voids, but HS never change. And we use this can calculate HS if you want to calculate HV because you want to calculate void ratio, right? So HV equals to current height. You can observe it with the sensor or a dial gauge, right? And HS we can calculate with this. Then you always know HV. How much HV now, right? Under sigma 1, sigma 2, sigma 3, you can always go to HV1, HV2, HV3 actually. So you can always calculate void ratio 1, void ratio 2, void ratio 3. And finally you got some pairs of data, right? Okay, now I give you a practice. You need to separate into group because I just got 5 pieces. You two together? You three? Please try your best to do this, right? This is the examination question I gave to students in the last examination. Yes, we will have a similar one in this examination. So if you don't know this, absolutely this is maybe I will increase it into at least 15 points. So it is actually a lot.
How many marks do we get for attendance?
Huh?
Attendance.
Attendance.
Tell me.
Attendance and homework together. How much do you want? Sorry, I can't.
40.
Yes, at most 40.
40.
40.
No, if you get this question, 40 plus 15.
Look at this.
Stop calculating.
Work on the question, work on the practice question now.
Sorry.
Do you want me to transfer to PowerPoint?
No, I want you to go back to the previous slide.
Ah,
Oh, yeah.
Be careful with, you can't directly copy this. If you copy this, yes, you can.
I'm just getting an idea.
But there are some other idea. The idea I talked is a little bit different with here. You should be careful with this is EI. Sorry. This is E note. In here, it calculates the void ratio change, delta EI. So it is not reflected in the void ratio at this stage. If you are stuck, just put up your hand and tell me, and I can give you some help.
Yeah.
It is better that you list those data. What is, if you know WS, ES, GS, gamma, W, you can list this data you know. Then you will know which data you should use to calculate another one. Yes, you can write it.
Okay, so here it says
way, right? Archway is not only one archway. You need to go to the archway in here, archway in here, archway in here, right? So actually, what is archway? Archway is h minus hs. Did you calculate hs? Yes, you got hs, right? And h, this is actually h. This is current h. H is always the current value. Yes, then you got archway, right? You know archway, you know each archway. You can mark a little bit in here. You marked archway, and then you know how much archway under each loop is there, and then archway divided the hs. That is void ratio, right? So you can plot in here. How was that? So HS is used. You must have got energy. Those down, those down. Area.
One.
This is a line. So everything is right. So as far as you know, that's it. You must know everything. So in an area, you can calculate HS. But in here, one thing you want to go to a void ratio, right? So what is void ratio? Void ratio is actually line ratio. So if you want to calculate void ratio,
This one minus
Okay, first of all, which one is that? Is this just H? This is H. Okay, if this is H, then which one is this one? This one. The one which is here. Because me, I was confused with the HB and HS, like, so that this is a given for each of them. Like I was wondering, this is the
This is height, not HS. You need to calculate HS. This is the final height. That is after each loading step, remembering the height is like this. That is the current height. Current height. After you compress to 0.1, but you calculate about the height. Here is that is 24.5. The height is decreased to 1.86. This is, yes, this is height. This height, right? The height of this is, you know, HS, we can calculate it based on the data. Yes, we can. If you use this minus HS, that is actually kind of different. Yes, you can find the height of change, but height change is not very helpful for your formulation. You want to know what is formulation under each loading step. That is actually under each loading step divided by HS. What is actually under each loading step? That is the total H minus HS, right? So as long as you already know what is H, right? Final H minus loading step and HS never change. Calculate HS, use this each one to minus HS, you got H weight on each loading step. Those H weight on each loading step, each one divided by HS gives average formulation. Then you can got 1, 2, 3, 4, 5, 6, 7 pairs of data.
One. Yeah.
That's not used after packaging. That's the kind of
And they post. I love
yeah, what is page what is the one that but then
Time is random. We will find the word here.
and they come and check what is that?
We were coming at 8 before.
But they understand. So just like change.
We have seen we didn't change it, right? I'm saying to change it.
I think we're doing that. Yeah, like, I just copy from the video. Copy